definition?
Yeah.
Not only the magnitude, the vector.
The vector, but only of one particular.
Oh yes, yes, yeah. That's a very good. Yeah, that's not the whole. Not yeah. No. This is at one particular point. If you wanted to measure the electric field at all points, you would need to do the same experiment over and over again at different locations.
Right.
Okay. All right. So with all that, let's go back to this expression. Okay. And so the vector r sub j is generic. It's any location in space. Okay. So again, we interpret this sum as a bunch of charges I that produce a force on j. Okay, so let's then establish a little bit of notation so it's easier to talk later. I'm going to say that in this equation here, the particles I, which are many, are called the sources because they generate the force, and the particle j, which is single, okay, is the test, or we can call it a probe also. It is the location where we probe our force or our field or whatever. Is that clear? Okay, so that formula is telling us that we have 100 I particles and one single J particle, and that J particle now I'm going to use it as a probe. So it has to be a small Qi, the Qj. Okay? So if in this equation I divide Fj over Qj, I have an explicit expression for the electric field at location r sub j. Is that correct? Okay, so let me write that because that's basically the beginning of everything else. So the important thing in writing that is to realize the simple idea that r sub j is a very generic location. Okay, so for that reason, we don't really need to write j anymore in this expression if you think about it. For the force, yes, because we have the charge, but now here r sub j is anything, is any location in space. So why don't I just call it r instead of r sub? Why do I need an extra j for that? Okay, for the i's, I need it because I'm adding in an I. But for the j, I don't need it anymore. R sub j is anything. So then it will be a simpler notation just to write that in any case, in a very general situation, the electric field at location R always will have to be of this form. Okay, so I changed a little bit the notation, but the electric field always has to be a sum of that type. There are some charges somewhere in space, I, and at any location R in space, it's going to produce this. Okay? So, now this statement is for all R's in space. Not for a single R in space, for all R's in space. Okay? One of the problems, and we will look at the same problem from a different perspective, is that there are many cases, very important cases, many applications in which we really don't know where the charges Qi are, but still there is an electric field. One very nice situation is the case of conductors, or in general the case of matter, not necessarily conductor, even insulators. If I have matter, a piece of matter that is charged, so for example I take a piece of glass from the shelf in the lab, or a piece of copper, and somehow I inject or generate charge on that object. Okay, I put charge, that can be done. Okay, so where did that charge go? Yes, how do I know?
Can you repeat that?
Yeah, so I have some object that I pick up in the lab, a piece of glass, I said, or a piece of metal, and I inject some charge. Yes, I can measure with my instruments that I put 1 coulomb of charge inside. That I know. I know how much charge in total I put. But where did it go? I don't know. I mean, does it depend on whether the object is round or elongated or rough? You know? Well, it may depend on many things, but the bottom line is that we don't know where they went. So not only, I only know the total charge, not only I don't know where the charge went, I also don't know how it broke up, how it was distributed. So in other words, I don't know.
It's not distributed uniformly?
Sometimes yes, sometimes no. Yeah, so for example,
What if the density of the conductor was uniform? Would it be?
No, this is a complicated problem. So for example, if you have a rod, you know, for thunderstorms, it turns out that most of the charge goes to very sharp points.
Really?
Yeah, I mean, but you have to, you know, so I'm telling you a fact that people have studied.
Where does the
How far is uniform?
like where does it go after it hits the rod?
The ground.
Yeah, yeah.
Oh, so there's a line going to the ground.
Yeah. No, there is not a line. The ground is conductor.
Oh.
I mean, if you have to do a line to
No,
the
I'm
ground.
saying on top of the building. It's on top of the building.
Oh, then if this is on top of the
Yeah.
building in your house also, there are cables that connect to some ground in the house or in the building. Yeah, here
But how much?
I suppose.
That's like super high voltage, you know?
Yeah, but it doesn't really matter. There's not much current though.
Oh, okay.
Yeah. So in this, no, not too much. Yeah. So in this building there must be some big ground down there in the basement or something like that. Okay. So. Yeah, so, but depending on the problem, problems could be very complicated, that we in general don't know what QI is, meaning how it breaks down in pieces, and where they are, okay?
Wait,
So,
for a sphere, does the charge go to the surface?
yeah, if you have a metallic conducting sphere, if it's conducting, because if it's not, you can have a patch, then we will show later that it will be uniformly distributed on a...
Is there a limit to where the object becomes uniformly charged? Like if you charge the crap out of it? Or not?
If you charge the top?
If you charge it, if you give it a lot.
Oh, okay. Okay, fine. That you're being recorded. You can. Yeah, eventually, if the field is very, very large, you can break the material. Yeah.
I never knew that.
And also what it means to go to the surface of the conductor. There is a limit of what the surface is, because you know it's not. But okay, let's continue, because there is a lot to do. Okay, so for that reason, there are only a few situations in which this type of approach is interesting, okay? And we'll review some of the simple problems that you've done before, just to use notation and to emphasize a few other things. For example, okay? We can, so for example, if you have in many situations, charge does distribute uniformly, but not always, okay? And then if it doesn't, then you would have to solve a different problem. But for example, one interesting problem is the problem of a charge line that everybody has seen already before. And even more important is the charge on a ring, okay, a ring of charge. So we'll discuss those. One result that comes out of that is very important to understand the connection. Eventually we'll need it later for the electric fields between different materials. Okay, so that's a starting point to start to study those things. So, so for the time being, we are going to consider a line of charge uniform and a ring of charge uniform, just to practice and emphasize some concepts and the notation. Okay, but the point is that we are going to spend very little time on those examples. We are going to move fast because in many situations we really don't know where those charges are, and we need to figure out other approaches. That's what it's going to be. We are going to spend a big chunk of the semester doing that.
We need to figure out what? You said we need to figure out.
We need to figure out methods to study problems in electricity where the charges are not known. How is that we can deal with that? There are many examples that I gave you, like those kind of things. How do we solve those problems when we don't know where the charges are? There are nice ways to deal with that. So we are going to spend more time on those problems than on these simple ones. But let's get started with this first. All right, so before we continue, so since we don't know what reality is, in the real sense of the word, so we're just going to play back and forth for mathematical convenience what is better for us. Okay, what I mean by that. So you can argue, well, if I have particles distributed in a material, they are not going to be located exactly at certain locations. Maybe we can think of it as a fluid better. Okay. Well, so somebody else will argue, no, but I mean, you have atoms and you have electrons. Okay, so you can go back and forth and spend the rest of the night arguing one way or another. But the fact of the matter is that to talk about discrete charges or to talk about continuum could be convenient depending on the problem that you are trying to solve. That's the bottom line. Okay, and for that reason, we want to have all the different tools available. So it is a very simple matter to convert this expression into a continuum expression, as you guys know. So let's just do it for a quick review and also to establish notation. So what I'm going to do is this. The letter R, the position vector R, I'm going to reserve for probe, for observation point, for test, for where I measure. The letter I, I'm going to reserve it for the generators, okay, the charges that produce the field, okay, the sources, okay. If I deal with a discrete situation, it's going to be R sub I. But if I deal with a continuum, then I'm going to change the notation because I cannot have an index I anymore. So I'm going to call it R prime. Okay?
Wait,
so
test charge?
the test charge is always going to be R, always, like here. But the sources are going to be either Ri in the discrete case or R prime in the continuum. Okay, and if we stick to that notation, then things will be easier later. Okay, so then basically, depending on what type of description I want, I'm going to have that, for example, or I may have this. So R, I told you, same. But Ri now turns into R prime. Okay, and as you know, to go from a sum of very packed charges, I, to an integral, I use the concept of a Riemann integral, and so this Qi, so I have a volume, and I divide the volume very finely in three-dimensional pixels. In each pixel, I'm going to have a charge Qi equals to the density of charge times the volume. Okay, so let's use rho as usual for the density of charge located at some place that you're going to tell me times the volume. But I'm going to leave it there. So what should I put inside the rho? What variable? R or R prime? Given that R prime, exactly, because it came from the charge I, what was varying, so this is my source, R prime, okay? So if you want to emphasize, this is an integral in volume, the density times the volume gives me the charge, but maybe you prefer to put a prime in there, okay? Just to remind yourself that in reality the integral is in the variables R prime, okay? So just a question of notation, more notation, okay, it depends. So sometimes people like to do this. Okay? Some other people like to put a 3 in there to remind that it's a 3-dimensional element, not a 2-dimensional or 1-dimensional, but whatever. So we'll see in the context what is better for us, okay? But for now, I think that's good enough. And then, okay, so this would be useful if we are dealing with a distribution of charges that is not uniform but continuum in a 3-dimensional object. Okay? Turns out that the first 2 examples we are going to do are on a line and also on a surface, and so, well, that's not going to be convenient, so let's rewrite that this way. And then we'll just have a menu to pick from whatever we are doing. Oh, I'm sorry, this is in a volume V without the prime, because this volume V is, for the variables R, is fixed. Okay? So this one would be on a surface S of, same story now, R minus R prime cube times R minus R prime. And then over here, for the charge, instead of doing rho times dV, I'm going to do sigma times ds. Okay, and then basically the definition of sigma is the charge per unit area, so on. Okay, and finally, another way would be 1 over 4 pi epsilon 0 integral of the line charge lambda dl prime r minus r prime cube okay, and then this one would be on some curve C.
What is lambda?
Lambda is the charge per unit length, coulombs per meter. Okay, so those